Hi everyone. Just going over, or I guess continuing today with a brief online lesson on Pythagorean theorem. It's going over the basic principles. We started this conversation in our Minds On activity yesterday in the discussion board where I asked you to create three to scale squares, a 5 by 5, a 4 by 4, and a 3 by 3, putting them together to create a right angle triangle. It should look something like this here. And the idea was to figure out what are some of the basic properties of a right angle triangle, which most people figured out. There's two line segments here. There should be a right angle symbol here that create the right angle. And then there's one long side that connects those two arms, which is what's called the hypotenuse, for those of you who looked it up. So what we're going to talk about today is the Pythagorean theorem. Pythagoras was a philosopher who figured out that if you create a square using each one of these arms, the square's area, each square's area relates to one another in a very unique way. So we're going to start by labeling the squares A, B, and C, okay, for the teal, orange, and purple. So he learned that the hypotenuse, the area of a square created from the hypotenuse, this part of the triangle, is equivalent to the areas of the squares of A and B. So again, A squared would be how we figure out the area of a square. So A squared would be 3 times 3. That would give you the area, which would be 9 centimeters squared for the teal square. Same thing for B. And then we can see the final formula down here is A squared plus B squared. So these two areas added together equal the entire area of the hypotenuse square. Where this can be useful, we talked a bit about the different places in real life that we see right angle triangles. And we'll continue kind of learn about this and review some other real world examples as we move throughout the work this week. So first and foremost, we're actually going to guess, not guess and check. We're going to solve this problem. We have all of the provided details that we need, A, B, and C. We do want to, in fact, prove, though, that A squared plus B squared equals the area C squared. So let's start with A, which is 3 squared. It's like saying 3 times 3. So the area of this square is 9 centimeters squared. Second one is 4. So 4 squared is 16 centimeters squared. So 9 and 16 should equal whatever the area of C is. So C is 5 squared, which is 25. So if we do the math below, A squared plus B squared should equal C squared. 3 squared plus 4 squared should equal whatever 5 squared is. That means 9 plus 16 should equal 25. And it in fact equals 25. So that shows that the theorem works in this regard. For an example 2, we're going to go over 2 more examples of questions you might see throughout the week. We do have independent work coming on Wednesday. So in this case, you've got A and B, but you don't have C. So we always start by writing our equation. I have it color coordinated here just to help you out a little bit. A squared plus B squared equals C squared. So we plug in the numbers we know. 5 is A, so 5 squared plus B is 7. 7 squared should equal C squared. 5 squared, 5 times 5 is 25. 7 times 7 is 49, which equals 74. Now 74 is the area of this entire square. So we want to bring it back. Oh dear, I got Siri coming up here. Sorry about that. My bad, I have no idea. It's like not exiting that easily. Anyway, so 74 is the area of C. We want to figure out what the side length of the hypotenuse is connecting these two arms. So obviously we want to bring it back to the number it was before we squared it, so times it by itself. So the opposite of squaring something, or to the power of 2, is to square root it. So when we square root it, this little symbol on your calculator, it will take 74 back to the smaller number that when you multiply it by itself or square it, it became 74, right, to figure out the area of C. So when we do that, I've rounded to the nearest hundredths, as we usually do in class, 2 decimal places to the right. It might be off by a couple thousandths, but for now we're going to keep it simple, keep it 2 to the right to the hundredths column. So Upon completion, we can see that a right angle triangle with the arms A and B 5 and 7 centimeters would have a hypotenuse of 8.6. Very useful if you're building anything that requires a proper right angle, whether it's building bracing or double checking your work. This can come in handy. Example 3 is a little more challenging. It requires balancing the equation. We did this a little bit with variables in algebra, and you may have worked on it in previous years, but we're going to do a bit of work on that today. So that's where you can reorganize and restructure a question to figure out what a variable is. And a variable is a unknown amount. So in this case, we know C, we know B, but our variable will be A. We have no idea what A is. So A squared plus B squared equals C squared. So we're going to plug in the numbers that we know. We don't know A squared, but we know 6 squared is B, 9 squared is C, and we'll solve those. 6 times 6 is 36, 9 squared is 81. Now, to balance the equation out, if you remember, we want the variable to be by itself. We want to get rid of everything in the equation we can so that the equation will equal A equals and then an answer. We can restructure this question by balancing it, reworking it, and eventually having it so that the equation gets dwindled down to what A is on its own. Some of us might be able to do this with mental math, but in case we can't, this is just a way that, again, balancing the equation is a good strategy to solve it. So we want A by itself. So we can take anything away from this side of the equation as long as we do it to this one. It's called balancing it out. If we take 36 away from here, that's okay. We just have to take the same amount from the other side. So our answer gets smaller while our question gets smaller here. So if we get rid of 36 on this side, and then we minus 36 from 81, we're left with 45. Now 45 is the total area of A. Okay, we want to bring that back to what the side length is, or what it was. To get rid of the squared on A, we could square root it, kind of like doing the opposite. Instead of adding 36, we take away 36. Instead of squaring something, we square root it. So we would do that to the other side. So A would actually equal whatever the square root of 45 is. And it brings us to 6.71 centimeters, again, rounded to the hundredths. And if you double check that and plug in the numbers, 6.71 squared plus 6 squared should equal 9 squared. Or that is to say that 45 plus 36 does equal 81. So yeah, you have independent work that will be assigned tomorrow. Ask any questions in the discussion board that will be posted today. Yeah, best of luck.